All right, so the last type of limits we're going to find are for specific types of functions in which there are some other options. So far we've used a graph to find a limit. We used a table of values, and we've looked at piecewise functions and then specific functions or cases in which limits do not exist. So today we're going to look at two types of functions in which, although graphing is not going to be an option most of the time, we can't try direct substitution, and a table can be somewhat of a pain. So here's what we're going to do. We're going to look at what's called the dividing out technique and the rationalizing technique. And both of these start out with rational functions. So you're looking at a fraction. Okay. The first one is the dividing out technique. So if you have the limit of a function that's a rational function, so top and bottom both fractions, and you can actually do some factoring and cancel, then this is when you're going to use what we call the dividing out technique. Okay. Now, good news is there's no dividing really involved. You'll see what's going to happen after we do our factoring. So let's start with this limit as x approaches -3 of x squared plus x minus 6 divided by x plus 3. If you went ahead and tried to try that direct substitution, and I would encourage that, please go ahead and do that first because it's the most expedient use of time. So if you go ahead and try that, we would have 9 minus 3 minus 6. So we'd get a 0 in the numerator, and we'd have a -3 plus 3, so a 0 in the denominator. And hopefully you remember that's called that indeterminate form, which means we have to try something else. So direct substitution is not possible. Now, you could go ahead and make a table of values, but we're also going to look at this new option, dividing out technique. In looking at these the numerator and denominator, hopefully you realize that there is some factoring we can do here. So that numerator is actually something that will factor. So I'm going to rewrite this problem. And although I'm not going to be a huge stickler for notation, when you take a calculus course, it's kind of a big deal that you don't lose that limit out of the problem until you have actually found the limit. So just don't keep writing equals. Let's keep that limit in our expression. Okay, so I want to factor x squared plus x minus 6. So factors of -6 that add to be 1 would be +3 and -2. Okay, so top is factored. Bottom won't factor because it's already a linear factor. Now, what's cool about this expression is that I see an x plus 3 and an x plus 3, and hopefully we recognize that those would just cancel. Now, think about a rational function in which something cancels from top and bottom. You remember what that does in the graph? That creates a hole. So as a function value, that function doesn't exist at that point. In terms of a limit, I don't care. I just want to know what's going on around that value. So by taking that hole out, I have created a new expression in which I think I'll be able to just use direct substitution. Okay, so the hole is kind of being negated, and now I get back to a more simpler expression in which I can just go ahead and do my direct substitution with the -3. So now the limit as x approaches -3 of whatever is left over equals -3 minus 2, which equals -5. Okay, does my function exist at -3? No, that was that hole that we canceled. Do I care? No, because I'm just looking for the limit, which is telling me what the function is approaching around -3. Okay, so that's your dividing out technique. If something looks factorable, factor it, see if something will cancel out. Now, the second type of rational function that you're going to see looks a lot different, and you can see that in the example down here. So what's going to stick out here is that, again, it's a rational function. You've tried your direct substitution and gotten 0 over 0, so your indeterminate form. Now, the key here is, do you see a radical? I shouldn't put X. Do you see a radical in the numerator? If you see a radical in the numerator, what we're going to try is what's called the rationalizing technique. I actually don't like the name for this because this is rationalized. The radical is in the top. So really what we're going to do is we're going to unrationalize. Let's rewrite this expression and get that radical back to the bottom where it probably started. Okay, we will do that by multiplying by the conjugate. So this time, though, we're going to look at the conjugate of the top. So the conjugate of my numerator would be square root of x plus 1, and then change the sign, plus 1, top and bottom. All right, remember, whatever you do to the numerator, you have to do to the denominator. Okay, so I'm going to multiply this out. Again, don't lose the limit. We haven't taken the limit yet. So x approaches 0. Now let's think about foiling this. When I take the square root of x plus 1 times the other square root of x plus 1, just leaves me x plus 1. The outer terms are going to be the opposite of the inner terms, so they'll cancel each other out. And then the negative 1 times the positive 1 should give us a minus 1. Much simpler. The denominator, I would suggest you don't multiply out. I could go ahead and distribute that x, but I think you'll see why I don't want to do that here in a sec. So I'm just going to leave the denominator as my two separate factors. So x and then that conjugate, square root of x plus 1 plus 1. Okay, so I have used the conjugate in the numerator. Now, again, let's do some simplifying. So limit as x approaches 0. Looks like on top we have a plus 1 and a minus 1 that'll zero out. That leaves us a numerator of x. And in the denominator, remember that x that was hanging in the front? That's why I left it there. Okay, so now numerator and denominator have a single factor of x, which will cancel. What's left on top when I cancel the x? Hopefully you recognize it's a 1. Okay, so we have used our conjugate. We've done some simplifying. Now I want to recheck, will direct substitution work in this new form? So now can I go ahead and plug in my 0? Okay, numerator's fine because it's just a single 1 up there. Denominator, what happens when I plug in 0? I get the square root of 0 plus 1. So 1 plus 1, and that equals 2. So this limit is actually 1/2, which we never would have seen